Well, let's get started anyway. So last time we ended on this idea of the parallel axis theorem, calculating the moment of inertia of objects. Just to review a little bit, the moment of inertia of a single object, a single point particle at some distance r from the center from your 0 point, your center of rotation, whatever you want to call it, is just the mass times that radius squared, that distance squared. And if you have multiple objects, you can actually just, if you have multiple objects all measuring the moment of inertia from the same point, then you can just add them all up separately. And of course, if you have an infinite number of infinitesimally small objects, you can use an integral to do that. And we did that for the line, or for the rod, the thin rod. And you can do it for the thin rod about its center, and you get this result. The thin rod about its end, so now it's spinning around the end of the rod instead of around the center of the rod. You get a different result here. And you can do it for a disk. So when you do it for a disk, instead of picking a little piece of the rod linearly, you pick a little ring of the disk, and each ring of the disk going outward is going to add to this, and so every ring. And so you have to integrate this one slightly differently, because instead of integrating as a dx, a little piece of distance, you're going to be integrating a little piece of r and an entire angle. So you're actually doing a two-dimensional integral here. But you can combine, since you're doing the entire angle, since you're going all the way around 2 pi radians, then that part of the integral just becomes 2 pi. So you end up with a 2 pi r dr as your integration variable, essentially. And so that changes the integral, and then you get this result. And they do this for lots of different ones. This is how they did. This is how they calculated all the ones in the previous section, all the different shapes, is they chose different integration variables, and were able to set up an integral to essentially do a moment of inertia calculation using this. So anyway, in the end, that gives you the same. That gives you all these different formulas that we had in the previous section. Now, the parallel axis theorem is this idea that, let's see, where was it? Where did it go? It's in this section somewhere. I'm just missing it. Oh, here we go. So the parallel axis theorem says that if you have an object, like a disk or a ring or a rod or whatever else, and instead of rotating around like the center of the rod or the end of the rod, you move that rod out away from the center of rotation somewhere, and then it orbits in some way around some other center of rotation. Then you can use this theorem, which says that you take the moment of inertia about the center of mass of the object. So if it's a rod, take the moment of inertia about the center of mass of the rod. And it depends on which dimension you're in. So if you're talking about a rod is a very good example because it has a very different shape depending on how you turn it, right? If you turn it this way, it kind of looks like a circle. If you turn it this way, it looks like a line, right? But it's a vertical line. If you turn it this way, it's a horizontal line, of course. So it doesn't have a lot of symmetry to it in Cartesian coordinates. But if this thing is going to orbit around a point over here, and it orbits this way, standing up like this and going around like this, then you need to know the moment of inertia of this as it rotates around this axis. If it's rotating around this way, then you need to know the moment of inertia around this axis, right? If it's rotating around this way, so if it's rotating around this way, you actually need to know its moment of inertia around the end. But if it's rotating around, if it's rotating around this way, like going around like a spaceship or something, then you need to know its moment of inertia around this way. So it can be a little bit tricky, but once you figure it out, essentially what you're doing is you're trying to figure out which way it would be rotating if it wasn't orbiting. If it was just rotating on an axis, which axis would it rotate on? But that's what you need. You need that moment of inertia for the object first around its center of mass or around some other point on the object, plus the mass of the object times the distance that it is from the center of the orbit. And that will give you its moment of inertia in its orbit, right? So when does this happen? When does this occur? Well, if we go back up to this previous example of the barbells, and we want to know the actual moment of inertia about this, and we don't want to treat these these weights as like point masses, because they're not point masses, they're disks, right? So if we want to treat them like a disk, then we have to figure out the moment of inertia of a disk as it rotates around the line through the center of it, right? Because that's the way it will rotate around if it's the barbell. And then we have to take the mass of each of the disks and multiply it by the distance squared to it and add those two things together for the parallel axis theorem. So that is what the parallel axis theorem is all about. So let's take a look at an example. Here's an example of an object. This is what they call a compound object because it's made of two different shapes. It's made of a rod length L and then a disc of radius R on the end of the rod. So what is the moment of inertia of this whole thing? Well, first of all, we have to think, what is the moment of inertia of the disk? We're going to first calculate the moment of inertia of the disk. So to do that, since the disk isn't rotating around some point on the disk, it's rotating at some distance away from this point A, then we have to, because of that, we have to take the moment of inertia of the disk around its center here. If this is rotating around this way, then it's kind of like the disk is rotating this way, right? On that axis down the center of it. So we have to take the moment of inertia of the disk around its center, which happens to be 1/2 the mass of the disk times the radius of the disk squared. That comes from looking on that chart in the previous section. Then we have to take the mass of the disk times the distance between this center and the center of the disk. Well, the distance between here and here is the length of the rod plus the radius of the disk. So you take the length of the rod plus the radius of the disk and square it. That's the distance squared. So this right here, this parallel axis, calculates the moment of inertia of the disk going around and around. It still doesn't include the rod, though, right? So to get the total moment of inertia of that whole system, we have to take the parallel axis moment of inertia that we just calculated for the disk and add on the moment of inertia of the rod. The moment of inertia of a rod rotating around its endpoint is 1/3 times the mass of the rod times the length of the rod squared. So we put that in there, and then we add all those together to get the moment of inertia with the parallel axis theorem for the disk. So this is the moment of inertia for the disk orbiting around that point, and this is the moment of the inertia of the rod rotating around its end, added together. So here's another example where you have a merry-go-round, right? You have a merry-go-round, which is, they're going to approximate it as a disk and then a child on the disk. Well, this one's actually easier than the previous one because you don't actually have to use the parallel axis theorem if you're gonna approximate the child as a point mass. So they do that. They say they approximate the child as a point mass since the size and the size of the child and the mass of the child are much smaller than the merry-go-round. So they're just going to calculate the moment of a spinning disk for the merry-go-round and add it to the moment of a point mass going around and around in a circle. And that's easy. You look up the spinning disk, and a point mass going around and around in a circle is just the mass times the radius squared again. And they do that for both, and it's really quite simple. However, if you wanted to be more correct about this, if you wanted to be more, if you wanted to get a more accurate representation of the moment of inertia of this, you would have the bottom of the merry-go-round being a disc rotating, right? You'd have the middle of the merry-go-round being a cylinder rotating, right? For each one of these bars, it would be a bar rotating on its end or a bar going all the way through, rotating through its middle, right? For each one of these bars, it would be a bar that's some distance away. So you'd use the parallel axis theorem because it's orbiting. These bars here aren't actually connected to the center. They're orbiting around the center, right? You could even do these bars that are in here at an angle. That would take some math we haven't done yet, but you could do it. And then the child himself, you might approximate the child instead of as a point, you might approximate them as a cylinder or a box or something, right? And then you would have a whole bunch of things to add together. You'd have a couple of parallel axis theorem things to do, and eventually you could put together a moment of inertia that approximates this a little bit better. Not something we'll do necessarily. So here they do an example where they have a rod instead of a disc on the end, they have a solid sphere. So a solid sphere has a different moment of inertia, and since it's going to go around and around at some distance away from the center point, it's like it's orbiting, and that orbiting is now going to make us use the parallel axis theorem. So the general rule of thumb when you're dealing with moments of inertia is to say, is the object rotating around some point on or in the object? If it is, then probably you could use a formula if it's going through the center of mass of the object or rotating around the edge of the object, on the surface of the object. Because most of the formulas are like that. However, if it's not on the center or the edge, if it's somewhere in between, or if it's further, if it's outside the object, then you might have to use the parallel axis theorem to figure out what your moment of inertia is going to be. Since this sphere is rotating at a distance away outside of the sphere, and it's orbiting around here, then we have to use the parallel axis theorem to figure out the I for the disk. The rod, however, since the point of rotation is sitting on the rod, we can use just a formula for the rod. So we'll start with the parallel axis theorem for the sphere. So to do the parallel axis theorem, we calculate the moment of inertia of the sphere around its center. So the moment of inertia of the sphere is 1/3 times the mass times the radius of the sphere squared. And that's what they do right here. 1/3 times 2 times 0.5 meters squared. And then you have to do the parallel axis thing, which means you take the mass of the sphere times the distance that the sphere is from the point of rotation, which is the length plus the radius of the sphere again. So they do that here. The length plus the radius of the sphere again. Oh, sorry. I actually lied. It's 2/5 mass of the sphere. I skipped a line and wasn't looking at what I was doing. It's actually 2/5 of mass of the sphere for about the center of the sphere. And then for the parallel axis theorem, it's this one where you add the length of the rod plus, and it's the same as the disk example before. But then we also have to add on the moment of inertia of the rod, which is 1/3 the mass of the rod times the length of the rod squared. You plug in your numbers and you're good to go. In part B, what do they want to know? What is part B? Oh, this one. So this is part A where it's rotating around this point, right? In part B, they rotate it around this point. So in this one, all you have, since it's rotating around the edge of the sphere, you could use the parallel axis theorem to calculate the rotation of a sphere about its edge, but there's also, I think there's a formula for it as well. But they actually go ahead and calculate it using the parallel axis theorem. So this, the 2/5 m sphere r squared, is the moment of inertia of the sphere around its center. And then you take the mass of the sphere, you add to that the mass of the sphere times the radius of the sphere, because that's the distance that you've shifted the rotation point. So it's just r squared instead of r plus l squared. And then, so that's the parallel axis theorem for the sphere rotating around its edge. And then this is the moment of inertia of the rod rotating around the other end. It's the same as it was in the first one. You add those together and you get a different moment of inertia. And it's lower because the mass of the sphere is much closer to the point here. Excuse me. So in this problem, we have a rod swinging back and forth like a pendulum, right? And they lift it up to a certain height at a certain angle, 30-degree angle, and that means it goes up to a certain height here. And then they let it go and they want to know what is the speed going to be here at the bottom. Well, you could think of this in terms of kinetic energy, but it doesn't necessarily work out that well because there's two kinds of kinetic energy here. There is the rotational kinetic energy in addition to the linear kinetic energy. And if you don't take the rotational kinetic energy into account, it will not work. And that's true in real life in this situation too. It's not just theoretical. It's very much true. So you have some potential energy when you lift it up to here, mgh, whatever this height is, which you can calculate by using, using trigonometry here. You have a triangle right here, and the angle right here is 30 degrees, and this distance right here is going to be equal to whatever distance it is out this way, or whatever. However you want to figure the length, the height, you can also do it using this triangle here, or even this triangle here if you want. It's up to you. But you're going to get some height here that you've lifted it to. Once you've lifted it to some height, and it's actually quite important to figure out the height of the center of mass of the object. So that's what they do here, because you want to know the center of mass is going to change height. But anyway, the point is that you're going to have a change in height or a change in potential energy, and that change in potential energy is going to equal your change in kinetic energy. But your kinetic energy is going to have two components. The 1/2 I omega squared plus 1/2 mv squared. And both of those have to be taken into account. So change in potential energy equals change in kinetic energy. When you do this equation, you have two kinetic energies, the I omega squared and the, let's see, where did they put it in? Oh, actually, there's no linear kinetic energy because the center, this side is not moving, so it is just rotational kinetic energy. So they end up with mgh equals 1/2 I omega squared, and this this 1 minus the cosine theta is the result of the trigonometry. Sorry, it's going too fast. From this right here, from the height. So that's essentially your height difference that comes out there with the L over 2. And in the end, you're able to calculate omega from this. So it's essentially a conservation of rotational energy. You have change in potential energy equaling the change in kinetic energy, solve for omega. So how would this change? How would we change this so that it would include both rotational and linear kinetic energy? If this object, if the pivot here of this pendulum was moving forward, then it would also have linear kinetic energy. So if the whole system was moving forward, or moving backward, or moving in some direction, some linear direction, then it would also have the linear kinetic energy involved. And that takes us to rotational dynamics, 10.6 torque. So I actually don't want to go on to study torque yet. I want to answer any questions that you might have about the homework concerning calculating moments of inertia, rotational kinetic energy, going back and forth between the different rotational and linear variables. Have you done any of the homework involving those things?
I haven't as much of the homework.
Okay, so then what I'm going to ask you to do is spend some time looking at the homework right now. If it has anything to do with torque, angular momentum, Forces, accelerations, I don't want you to deal with it. Only things that are moments of inertia, kinematics, anything not involving torques and forces.
So basically 10.1 through 10.5.
Yes, the stuff that's in 10.1 through 10.5. And then we'll come back to it to cover, like I said, I would prefer that this chapter be split into 2 chapters at least. But I didn't write the book, so I might have to rewrite the book. All right, so I'll leave you to that. And if you have any questions, come and talk to me.